Okay, you know how to find this. This is in course modules, last week of class quiz. Cool. This is the schedule. Today we're going to do exoplanets. Okay. We're going to switch 2 weeks or 2 classes of exoplanets into one. So we'll just talk about the fun stuff. That seem reasonable? And then on Thursday, we'll talk about whatever is the most popular topic. So if you haven't filled this out and you want to have a say, you're welcome to do so. Oh, look at that. Got 10 more. That's great. Right now, I can tell you that When We Left Earth is winning. But if you have a particular care, you can add that in there. And then if I see it show up, maybe I can. So someone said like nuclear fusion, and that actually has a lot to do with radioactivity. So I added those together. Any questions before we begin? Yeah, on Thursday. This is here. Oh, fuck. There. So here's information right here at the bottom. Cool. So you've done 11 homeworks, right? On Thursday, you will return the clickers. I hope that you all have them still. Because if you don't have them, even if the box didn't survive, that's okay. The box is not the important piece of hardware. So you signed something when you took it from me, which says that you'll return it or you'll let me know that you're going to give me money. Otherwise, you'll get an incomplete regardless of how you do in the class. I know, harsh, right? Okay. But that's the only way that we don't lose a ton of money. Okay. I got rid of mastering, so you didn't have to pay for that. But homework was a little fucked this year. I'm not gonna lie. So I have learned some things about like how to teach this class better, I think. I hope that most of it was helpful. If it wasn't helpful, I hope that you expressed what wasn't helpful in the SOTIs as well. So let's see how many people did. It's not bad. It's almost 50. I said you had to get above 50 to not have a final, right? They're outliers. No, so we don't have to do that. So I was thinking for the last thing, we won't have class during finals week because you never do. But I was thinking that we would have one last homework. It doesn't really make sense to do a check-in because I'm still grading your current check-ins, right? They happened late, they went in late. So what I'm going to do is I'm going to assign one last homework. Is that fair? You want to see what it'll look like? Okay. It's cumulative. Wow. Okay. So it's 5 questions. But it is something like a creative scientific writing homework. I want you to design a solar system. You have to justify your actions and describe how the choices that you make at the very beginning impact the choices that occur later on. So at the very beginning, I will ask you, I know you hate reading. Please read this piece. Okay? A minimum of 1 paragraph per answer. Okay? Ideally, more. The more, the better. The more that I hear from you, the more that I understand you understand. So there is like several questions in the first question, right? See all the question marks? Respond to each of the question marks, please. Add more, right? Tell me what you know. Does that make sense? People like this idea? Wow. Not just make up something, right? So it is make up something consistent with the rules of planetary science we have learned about this semester. So if you make a change, you have to justify it. And you're allowed to make changes that you want. So you could start off with a composition that says, I only have ices in this very strange solar system. Here's what it would look like, right? or I only have rocks in this strange solar system, this is what it would look like. But you have to explain how. That make sense? Do we like it? Yeah. No, this would be yeah, well, I guess. You going on vacation? Yeah. So I leave Thursday. I have a conference in DC, so I won't even be here. I know. So I'm beginning to think that maybe we just email me 80 emails. No, yeah, that's what I mean. Yeah. I can make an assignment that you submit it. That's the same to me as email. I get 80 emails when you submit. Um, so I will point out a few things. Okay. You can ask questions. You can work with other students because it's homework. You know, if you feel like you don't really understand something, you want to chat with your friend. You can reference the textbook or the lecture slides. That's perfectly okay. Do not copy and paste Google or AI searches. Okay. I hopefully have demonstrated that it's a helpful tool, that you can get some feedback on what you're saying, but it doesn't always know what it's talking about. And in this particular circumstance, it will do poorly. Okay. It will predict what the most likely next sentence is that may have nothing to do with what you're talking about. Okay. You're welcome to use it. Read it and understand what it says. Right? It's like listening to your friend. You don't know if they're full of shit. Right? It still needs to be your work. Does that make sense? Okay. So everyone likes this. No one hates it. Raise your hand if you hate it. Democracy. Let's go. All right. So that leads us back to this. So we'll have one class on exoplanets, and I'll show you some solar systems that exist, or I'll say planetary systems that exist outside of our solar system, right? And then on Thursday, I would love for you to come to class. We'll do something that people are interested in. If you say, no, that's okay. It's your life. And I do need your clickers back though. So at the end of that class, please turn your clickers in. Okay. Questions? Yes. Yeah. At the very end of class, I'll drive to the airport. Yeah.
That homework is due 13.
Yeah. So this last homework will be due. Yeah, here. Whatever Friday is on finals week. And I'll just make an assignment or whatever it's called that you can turn in. Yeah, it'll be due on Friday. I don't know if more time is better than less time. I know the longer you give people, the longer it takes them to do it. Right? All right, let's go. Nope, not that one. That's rockets. Okay. Real or fake? Oh, fake. Fake. Why do we know it's fake? Because what? Sun is so close, right? And we can't see any other stars in detail. We can only see our sun. That's good, right? Okay, so just to recap, let's form the whole solar system. Okay, what's the first stage in forming the solar system? That would be the universe, correct? But that's too big. Yeah. Yeah, so you have to start with a gas cloud and it's going to collapse. And then? Yeah, spinny boys, right? We flatten out into a disk and stuff condenses. So you have this material on the inside that's all rocky. And you have stuff out here that's all icy. And then the hand motions or no? Yeah, they smack into each other. That's accretion. Stuff smacks into each other. And if you get big enough, how big do you have to be? 10 to 20 times larger than the mass of the Earth. Then you can grab gas. Okay? And you get to be big, like Jupiter sized. And then the sun says, and it blows away all the gas. Okay?
How big do you have to be in the Earth's grab gas again?
10 to 20 times larger than the Earth. And you may need that to build a solar system. Okay, cool. So we talked a little bit about strange things that you might not expect to find. And we also said that you don't expect to have a lot of large Jupiter-sized planets close to the star, right? That would be weird. They're supposed to form out past the frost line, right? Far away. Frost line in the solar system is about 5 times the distance that we are, 5 AU. Okay, so it'd be weird to find 6 planets larger than Jupiter at a distance smaller than Mercury, right? Strange. Okay, that's definitely not going to happen, right? Okay. Let me just. We're going to skip around with these slides, so I apologize here. Let's talk about other planetary systems. We can talk about why it's difficult to detect planets around other stars, and then we'll talk about them. Okay, so here is an example. This star is called Fomalhaut, and the way that we label planets, we're not special about it. They don't get cool names. It's just too many of them. So many of the stars that you see, they're just going to have numbers, and then the planets just have letters. And the order of how we find them, not the order in which they are in the solar system, is the designation that they get. Right, so if this was the first planet we found, we call it A. But there might be one that's closer, and that becomes B. We find it later. Okay. So why is it so difficult to detect stars around other planets? Sorry, planets around other stars. Yeah, they're real small. Hard to see small things, right? So like I can see all your faces, I can't see your pores, right? Okay, if I get very close, great. Then I can see the planets, right? Just like I get close to Mars, I can see the surface. But we can't get close. Stars far, right? We can do direct detection. There's certain ways to observe planets, and there's certain indirect ways to tell that they are there. Okay, so direct detection includes taking a picture or taking spectra. That's like when we use the prism, right? The continuum of light. Indirect measurements, we measure the star. Star is much easier to see. Star is brighter, right? We can see the star from very far away. So if we can tell the influence of the star, the planet on the star, then we might be able to be better at that, right? For direct detection, taking an image of a planet, I want you to remember maybe the very first week we talked about shrinking the sun down to the size of a grapefruit, right? And I had people stand at the front of the class, and I said, the sun is the size of a grapefruit, and the Earth at that same scale would be a grain of sand. How far away do we have to hold those two? Can I do this? My arms work? No. It's larger than my arms, right? It was like 50 feet. Okay? My arms are not that long. Okay? So the whole solar system fit basically from here to the observatory. Right? Pluto is at the observatory. So that's the entire solar system with all of the planets and the star, the size of a grapefruit. And where's the nearest star? New York, right? So that's another grapefruit in New York. And that's it. Right? It's a grapefruit on fire, but you know, okay. So imagine trying to see a marble, like that's a Jupiter, or a pinhead, that would be the Earth, next to a flaming grapefruit in New York City, right? So not easy. Okay. So let's also keep in mind, planet's smaller, and it's only reflecting the star's light. So a sun-like star is about 1 billion times brighter than the visible light that we reflect off of it. Does that make sense? Okay. It's easier to see in the infrared, so we do have pictures. So in the infrared, that is light that's given off from the heat of the planet. And we can see a better distinction between the two. Here you see a multi-planet system. We block out the star so that we can see any of the planets at all. And you can see this wonderful naming convention, B, C, D, E. Cool. You can see they're all going around in the same direction. That fits with our formation theories. They probably formed in a disk, right? Yeah.
What if there are 27 planets?
I don't know. That's a very good question. I would assume that they flip over to AA. You might get really lucky and then you might get to like name them, right? So you find some system which is insane like that, and you'd be like, okay, I'm gonna call this after like the Greek gods of mischief or something. Yeah, we just don't have enough creativity and there's too many things, right? Abundance of things, not enough like creativity. So we've only found a few planets by direct detection. Okay. Let's see if is this a video? Oh yeah, that's a version. Pretty cool. Let's have a look at some indirect methods. What is the sound of a fire truck going by? Is that correct? As an example, what's the modification that I would use to the wee wee woo sound? Can you tell when the fire truck is coming towards you without seeing it?
Oh,
What?
Wow.
It's loud. Yes, that's true. It hurts. That's very important. But also, does anything else change?
when the sound's going from.
That's true too. We have 2 ears. Let's say we only have 1 ear. You wouldn't be able to tell. The pitch of it changes, right? The sound of it coming towards you is louder and higher pitched. It sounds like, and as it goes away, it sounds like, woo.
Yeah.
Right? Pretty good, you know? Okay. Could have been a singer. This is due to something called the Doppler effect. Okay, we're going to talk about that really briefly. And this is the first way in which we see most of the planets around other stars in their ability to pull the star towards and away from you. Okay, so let me show you an example of the Doppler technique first. I hope this works. You know what's going to happen, right? Sound is coming towards you, it becomes high pitched. As it goes away from you, it becomes low pitched. Okay. So the way that that happens, hold on, is like this. Really advanced drawing, I know, incredible. So this happens with light. We think about the pitch of light as the frequency. So if you're a music major, you like, guitar or whatever, frequency and pitch, same thing. And as the star, let's say it's moving towards you, it will appear a little bluer. And if it's moving away from you, let's say you're over here and it's moving in that direction, it'll appear a little redder. So if for some reason this was a star and it was moving towards you and away from you and towards you and away from you, then it would appear to change colors back and forth. blue and red, blue and red, blue and red, blue and red, right? Stars do that. Stars do that because there's, let's say, a massive planet like this and a star like this. They're both going around each other, right? This one pulls on this one pulls on this one. And so even though the big planet is going around the star, it forces it to sort of wobble. And as it wobbles, it seems to move towards you and away, and towards you and away. Does that make sense? I explain that again, or does everyone get it? Did you explain it to your friend? Yeah.
Is this like brightness or like on the side?
Brightness is not going to change here. It's just going to be whether or not it appears blue or red. Good question. Okay, so here's what it looks like. Okay, so we talked about the fact that light appears at specific wavelengths, at specific locations in something like a gas. So let's say that this gas here, that's hydrogen. Okay? And if this line that I know should be right here appears a little redder, what do I know about the thing that is emitting this hydrogen? Go back one step. Yeah, more redder. It's going away from us. Okay? If it's bluer, it's going towards us. If it's redder, it's going away from us. So this is the same Doppler effect that we hear with our ears. As the fire truck comes towards us, all of those waves of sound, they get pressed up and it becomes bluer. Right? Similar here. This happens as I'm moving too, but we can't perceive it because I'm not going very fast, hopefully. Okay. So in this circumstance here, this object is moving. What? Farther with respect to what? Away from us or towards us? This red line become redder? Away from us. Even the blue line became a little bluer, right? What about these three here? Also away, right? The red line became even redder and the blue line started to become green, right? What about these objects here? What? Towards. So even though it's still red, it's less red. And this green line is way over here. This blue line is way over here, right? So this object is moving towards us, right? And now imagine that you have a little telescope on this star and you're watching your favorite line of hydrogen, okay? And it goes back and forth, back and forth, back and forth. That means that the star is moving towards and away from you, towards and away from you. Now, what you'll see, if you looked with your eyeball, let's say you could go and fly over, you'd see it going in a circle. But what you can see with the telescope is only the part where it moves toward and away from you, forward and away from you, right? Goes around in a circle like this. So you can only see this part coming towards you, then this part going away from you, right? And you can see that in the lines of whatever species you're looking at. That make sense? Everyone understands it perfectly? Prove it. Okay, 5, 4, 3, 2, 1. Okay. A lot of folks like, no one likes E because it's not present. Good. So I like that. A lot of folks like C and B, or sorry, D and B. So it seems like you saw that the shift, right? This shift is the farthest on this side, but this is the farthest on the other side. So it's really just some folks don't know which direction goes which, right? Okay. So let's go back a step. If the light moves towards you, it appears blue. If it moves away from you, it appears red. Okay. Anyone want to defend their answer? Yeah. Right. So this looks like it's moving more to the red side. This is the largest red shift. And we asked which object is moving away the fastest. The red shifts are away from us, and the biggest one would be the fastest away from us. So it would be B. Good. Okay, now we're experts. Okay. Anyone been on a freeway before? A freeway? Everyone been on a freeway? Okay. Look at this wonderful analogy. Red lights go away from you. Oh, that's not why, but okay. It's a manufacturing thing, but I'm just trying to point out the analogy. Okay. So this is the way that it works. So let's say, imagine this is some unseen planet. I can't see it. It's very dim, but I can see that really bright flaming grapefruit. And I can see the flaming grapefruit move forward and away from me, right? And as it does that, it sends light in this direction towards me, blue shifted, away from me, red shifted, right? And look at how good we are at doing it. We can measure motions as small as 1 meter per second with telescopes. So like if you had a telescope and like you're pointing at a person running at you, you could get their speed. Pretty cool, right? Yeah.
So the moment the star shifts the other direction when it's turned, we know what it does.
Yeah, right here, it's not, it's only moving to the left, right? Or maybe to the right. And so in that specific instance, it would go back to no shift at all, right? And then it would go over here, no shift at all, blue, no shift, red, right? So we can turn those individual lines, we can turn them into speeds. When it's moving fastest towards us right here, it'll have the largest speed. You want to see what the data looks like? This is a real star. Really, really cool names. I know, calm down. So this is HD 404208. And the B would be the first planet. A is the name of the star. Okay. And so we look at this star and we say, huh, it's wobbling funny. And we watch it and we watch it. You'll notice here the time is in days. Okay, so it starts moving towards us actually pretty fast, something like 25 meters per second. I can't run 25 meters per second, like cheetah speed. But it takes a while to do, and we watch all these little data points fill it up, and we watch it happen over and over and over. And then we can infer that there must be a planet that's tugging. That make sense? You can get a lot of information out of these. So this planet is going around the star. I can't see it go around. But how long does it take for that planet's year? How many days in that planet's year? What?
700.
750. How'd you get that?
It's day 0 and day 750 are the same spot on the speed.
Yeah, that seems reasonable, right? You could also go from like here to here, but then you'd have to subtract off these numbers. I'm bad at math, so that works. 750. So is this closer or farther than we are? Farther, right? Its year is almost twice, or maybe more than twice our year. Right? We learned a lot just from some dots. Okay. Want to do a harder one? Okay. Oh no. All right, let's try this one. And we'll learn about all of them. Just so I can prove to you how, when we talk about the planets, how we actually know any of them. Now, don't look at the right side, just look at the left side. These are all real planets with real data. HD is the Hipparchus catalog, the Hipparchus database. The number is the number of the planet, sorry, the number of the star, and then the planet's there. You hit this one? Okay, let's vote on 5, 4, 3, 2, 1. Okay. Some nice disparity in the answers here. I'm going to go ahead and erase one of them. I haven't said anything about eccentricity. I haven't talked about this yet. This is a red flag. It's not this one. But now most of the discrepancy is between whether it's closer or more massive. I want you to turn to a friend and ask them whether they know what's going on right now. Okay? If they don't know what's going on, turn to the other side and ask them if they know what's going on. If they still don't know what's going on, just raise your hand.
Oh, yeah. You see that, the one that we did before, it's like 2 days. This one, it's 60. Yeah, or
So, for example, the total speed for you is the same as the total. So here, the very top of the key, still less than 2, and then 1 is still less than 2. 1 and 2 is not. Okay. Let's revote. Pretty good, pretty good. 5, 4, 3, 2, 1. Okay. Yeah. a lot of people moved towards this one. One has a closer planet. Yeah, why do we think that's right?
So look at the one before this, and it was we mentioned that it was a little farther. Yeah.
Yeah, this one was 750 days, right? And you could just read that off from where it like repeated the behavior. And this one repeats the behavior twice in the same amount of time. So this one must be closer. Okay. We didn't talk about how much it's pulling, right? So if you have a bigger planet, do you pull more or less? More. Because, for example, I stand here on Earth and I'm pulled down to the ground. But if I go to the moon, right, then everyone bounces around like this, right? Gravity is less. Remember that? The video that I showed a long time ago, 15 weeks ago. Okay, so what's the difference between these two? 5, right? The mass here is much bigger because it's making the star move a lot more, right? This is the motion of the star. Star starts here at 0, gets pulled almost to 300 meters per second, goes back in the opposite direction. Right? These are big swings. Make sense? What's this weirdo one? Yeah,
The centric one.
it's an eccentric one. What's happening here is the planet acts like a comet. Planet gets really close, pulled really, really strong on it, and then it heads far away. Basically doesn't pull on it at all, and then pulls on it a lot. Right? Okay. We can see multiple planets. You imagine having to look at that? So there's 2 planets here. And this is real data again. This is time on the bottom, right? It's probably before some of you were born. I'm not going to comment on that. Here is the eccentricity. These are pretty eccentric planets. They're not quite like comets, but they're kind of like squish circles. And they have 2 different periods. So you see that there's basically one large one, and then there's a small one on top of it. And so we can see the wobble of the star, and we can distinguish between this sort of big up, right? This is the big one, the 1200 day one, and then one that's a little bit shorter than our period, right? Okay. So that is one way of detecting planets indirectly. And the first one we did that with was with this guy, 51 Pegasus B, the first exoplanet to be detected. This is the artist example. There will be no photos. Not that you can't take photos, but we don't have photos. Okay, is that clear? Yeah, okay. There's another way to detect the planet. This one you have a lot of experience with, okay? Which graph represents my hand passing in front of a candle? Now, not the motion of my hand, but I want you to notice this is brightness versus time. And yes, I drew these. So just imagine that you're watching a candle and I put my hand in front. I have 5, 4, 3, 2, 1. Okay, good. Not a very good trick. You're all smarter than me. That's great. Almost everyone picked this one. Okay. That's the same thing that's going to happen if I look up at this lamp and then I put my hand in front of it. It looks slightly dimmer for like a little bit, and then my hand passes by. So that's all this said. Normal brightness, something went in front, goes down, I get less brightness, and then it goes back up. This is what we use to detect planets. Okay, this is called the transit technique. And this only happens if the orbital plane of the planet happens to be aligned with you, right? So you can't see it if the planet doesn't pass in front of the star. But essentially what you have is you have a transit, and that means that it just goes in front of the star, and the total brightness goes down. So at this point here, you're measuring the brightness, the combined brightness of the planet and the star, right? Wonderful, wonderful. It goes down, and then it goes back up again. Right? And you get a second one, because at this point, you're watching the combined brightness of the star and the planet, and then the planet goes behind the star, and it goes down again. Cool. What can this tell us? Yeah. Yes. Okay. Great idea. More advanced than I was thinking. Something easier than that. How many planets? Certain. Yeah. Good. What property of the planet can we learn this way? Yeah, size. The size. My hand is bigger, then I can block more light. Right? So if my hand is bigger, that tells me the size of the object, tells me how much stuff I block. You're absolutely right, and we'll get to the atmosphere part because we have observations of exoplanetary atmospheres. Just pretty wild if you think about it long enough. Okay. You can get the mass from the wobble. Right? Can you get the mass in this orientation? Will it wobble in our direction? Let's think about it this way. You're all telescopes. This is the planet. This passes in front, right? So that definitely gives us the radius. Now, which way does it wobble? Yeah, towards us, right? We're wobbling like that. So I can get mass from the wobble to and away from you, and I can get radius from it passing in front. And now we get the good stuff. Density. Right? So what if I find a planet that's the same size as the Earth, but it's made of something that's as dense as water? Is that a good place to find friends? Probably not. Right? That's probably an icy object. Maybe at best. Right? Okay, so we had a telescope. They launched this thing called Kepler, and basically just looked at the sky for 4 years. And if you looked up at Cygnus recently, or you came to the observatory open house, we have the last one tomorrow, by the way. They just looked at the same part of the sky for 3.5 years. All they did, just watching every single star in there. If it changed brightness, if it got brighter or dimmer, they would just keep taking observations of those stars. And they were looking for planets, right? Did they find any? Possibly. Anyone know like about how many? 1, 10, 50, 100. About 10? No, way more than 10. 5,000 is about the right answer. Okay, so here's an example. This is HAT P7. So we can watch. I mean, you can see it, right? See where the planet is? Right there. Right? That's what Kepler gets. It's a lot easier. What's all this scatter from? What? Starlight is scattering why? Famous song about this. Very scientific. What? Twinkle, twinkle, little. Yeah. So stars twinkle in our atmosphere, right? Because of the air in our atmosphere, twinkling the star. When you leave, when you go into space, you don't have that problem. super easy to find small objects. Right? Okay. Here's another example. So here is the data at the top. Ooh, let me get rid of that. Go away. Oh God. How do I get rid of this? I don't know. Anyway, up there you can see this thing. That's that thing. That's the secondary transit. That's when it goes behind them. Okay. Pretty good. We're pretty good at this. You can find out exactly how big the thing is. In fact, you can find out exactly how massive it is. And then you can find out really fun stuff. Like, how do I remove this thing? Yeah.
Put it on the side, like, you can stay in that bar, then you go exit. That works.
Oh. Okay, so this is HD 209-458b. This was the first planet to be detected by the transit method. And the cool thing about it is it looks like a comet, but it is larger than Jupiter. It is so close to its parent star that it is evaporating. And it leaves behind this huge plume of hydrogen and helium gas as it goes. It's having a bad time. Okay. Okay. Next one. This is TOI 849b. Now we have some issues, right? I'm going to show you some objects and we're going to run into some word problems because this is 40 times more massive than the Earth. So they call it a hot Neptune. Okay, let's break apart what we mean by this. If it is really close to its parent star, we call it hot. So you might have heard the word hot Jupiter. Maybe you haven't heard that before. It is not our Jupiter, obviously. It's a Jupiter-sized object that's hot because it's very close to its parent star. They didn't come up with new words for that size of a planet. So we call them Neptunes. They're just not Neptunes. Does that make sense? We call them super Earths sometimes, or sub-Neptunes. It's very confusing. Okay, this one's really sick. It orbits its star within 18 hours. It is so close that the surface is 1,530 degrees Celsius. So it's likely molten. It was probably a gas giant at one point, but all of the gas has blown off. Right? So that is TOI 849b. There's more on my. Okay. Next. This is WASP 12b. These artist conceptions is all we get, right? We can't actually see. I can show you the data, just not as fun. It's not as pretty. So this is a close. We were talking about these planets here, getting too close and maybe making rings. Making a ring right now. So this exoplanet probably has about 3 million years left to live. And we can tell that it's losing material of its parent star. It's going to get torn apart. People like Star Wars? No, hate Star Wars. Okay, I found Hoth. I didn't do it, but I found it online. This is Ogle 2005 BLG 390. Great names, I know. This is an exoplanet that probably started to grow a Jupiter-like core. So it was in the process of grabbing all of this material. It had all of these icy compounds, but it didn't do it quick enough to start grabbing hydrogen and helium. And the hydrogen and helium got blown away by this star. And so it's really, really big, but it doesn't have any gas. But it's just ice. Very far from its parent body. Right? Okay. This is Kelt 9b. This is the hottest known exoplanet. Its surface temperature is 4,000 degrees. This is bright enough to see with your eyeballs. Yeah, don't stand on the surface. It is colored here. That's the star, by the way. It's here. Keep your eye out. red. Very close, very hot. Not a good time. You'll also see that there's a little evaporation. That's probably true. Okay. That's your HAT P7. We saw this one earlier. We saw the Kepler data, the actual data of this guy. And this one's a little funny. This one orbits its host star 180 degrees tilted from the star's rotation. So the star rotates this way, and it is like this. That's kind of strange. We know why that's strange. Our sun rotates like this, and we go around it in the same way. We even go in the same direction of rotation. This guy said no. The surface temps here, 2200 degrees C. These ones are really cool. They are so hot that they have rain that is diamonds. Yeah. So remember we thought about the condensation temperature of rocks and metals at about 1500 degrees? That happens here. So certain exoplanets, I mean, obviously you can never stand there and like collect diamonds, die. But they just have like water cycles of rock. Rock melts and then like rains out, and then melts and then rains out. It's weird. Okay, this is Corot 7b. This one here, Corot 7b, that's this planet star, or the planet's star. And this is the first super Earth that was identified as a rocky exoplanet. Okay, so you'll hear some stuff in the news once you start paying attention to it, like, oh, we found an Earth-like planet. Now, can we go live on Corot 7b? Let's say we created faster than light travel. No, why not? This is very accurate artist conduction, makes it look hot, right? But we need a little bit more than just, is it made of rock, right? We need to know if the surface is livable, because the Earth's surface was probably molten for the first, 100 million years. Had to cool off a little bit. This guy might be too close to the parent star. Might be really uncomfortable to live there. We want to live somewhere comfortable. This is Kepler 10b. Now you'll notice that this one is named Kepler. That spacecraft earlier was named Kepler. When a star is found by someone, they get to name it after the telescope. But you don't get to name it after you as much as you might want. And you can't buy stars online. Don't do that this holiday. Okay, that is just a certificate that says someone else took your money. I'll take your money for free. So this is Kepler 10. This is the 10th star that Kepler found. And this is the first planet that it found. So let me show you what it looks like here. This is the first discovery of an unquestionably rocky planet outside the solar system. This has a radius of 1.4 times the size of us, right? Its phase here, go ahead and look at how long this is taking. Its orbit's about 0.8 days. Not great. Okay. Probably has a lava ocean on its surface. Not a great place to live. You want it to be a little farther from its star. It's too close, then the surface is melting. Right? Just like your ice creams, chocolates, whatever. Here's the Kepler 11 system. That's pretty cool, right? Okay. This system has all of these dudes passing right in front of the star. And in 2011, they announced that Kepler had found all of these planets interior to Venus. That's 1, 2, 3, 4, 5, 6 planets interior to Venus. And they're big. Real big. Here's the Kepler system. All right. So this is them passing in front, causing little dips. Goes down. And you can see the dip from each of the planets. So Kepler B is shown here, all of the dips from Kepler B. Kepler, let's see if I can do my colors good. Kepler G is this deep one. See here and here. Kepler E is here and here. Kepler F is there, right? Would you like to live in this system? Yes? No, it's all within the orbit of Venus. It's probably really hot and uncomfortable. Okay, so let's hope they did better. Here's Kepler 16b. What does that look like? What? Hot? Yeah. So in fact, that is another star. I believe this is the Tatooine system. So this is one planet going around two stars. So these two stars, this big one, that's A. And this is B. They go around each other, and then Kepler 16b goes around both. That's pretty cool, right? So you would see sunrise, and one of them would come up, and then the other. And then it would go down, and maybe on a certain day, the red one would rise first, and then the white one. On another day, the white one would rise first, and then the red one. Rad, right? Okay, let's go to this one. Plenty more planets. This is 55 Cancri E. This one's pretty wild. So, it orbits 25 times closer to its star than Mercury, right? So this is the sun, and there's Mercury, and there's Venus and Earth, that's one. And this is the whole system for 55 Cancri. And this is 55E. So it is locked, just like the moon is locked to us. It always shows the same face to its star. They think it probably has a rocky core, and then it has a layer of water that is in this like super critical state, which is somehow both a gas and a liquid at the same time. It's like high enough pressure, high enough temperatures. So basically think about like a whole steam tank, right? You don't look there either. Too close. Okay. That's 55 Cancri E, artist conception, right? What the steam would look like. So you can see these like winds across it. So we see that similar type of wind across Venus at the very top of the atmosphere. So they think that's probably what's going on here. They thought this was initially going to be all diamond, and they were getting ready to send some planes, but that was thrown out. Okay. Here is, I think you actually saw this one already. This is HD 189773b. This one has winds at the top of the atmosphere that are about 8,000 kilometers an hour. That's fast. That's much faster than any wind we have on Earth. The atmosphere is hot. It's about 1,300 degrees. And again, molten glass. So liquid silica, which is glass, is just raining down at about 8,700 kilometers an hour. Fun, right? Okay. Here's K218b, twice as large as the Earth. 8 times the mass. We found water in its ice. That's kind of cool. Only problem is that it's very hot. But now we're going in the right direction, right? First, we found all these big, very hot Jupiters. And now we're finding more like rocky, wetter, cooler stuff, right? Let me tell you about Kepler 22b. That seems promising, right? Looks like clouds. Artist conception, maybe got a little ahead of themselves there. This is the 22b system. So we define something called the habitable zone, and it is horrible because it makes you think that all you have to do is live in that little window and you're good. But I want you to notice for our system here, that's Mercury, Venus, Earth, and Mars. The so-called habitable zone includes 2 planets that are clearly not habitable, right? So Mars is here, can't live there. And Venus is right on the edge, can't live there. So it's not enough to say that it's in the habitable zone. We have to know what the surface geology is like, what the atmosphere is like, right? But this guy's pretty close. Pretty close, right? So the temperature looks good. a little too close comfort, but if it had liquid water, maybe it has a carbon cycle. Maybe it has oceans. Right? This is Kepler 186f. This is the first Earth-sized planet with a rocky composition in the habitable zone. So that's just gratuitous. We don't know that at all, but it looks cool, right? This is this picture. That's the Earth. That's the location of Kepler 187f. Pretty cool, right? And then, crazily, just like a year later, they found a second one. 452b. With an almost identical star, only slightly bigger. Cool. This is the 11F system. So eventually we start finding some stuff that is significantly larger. There is a class of planets that we call gas dwarfs. Okay, not gas giants. So they are smaller than Neptune, but bigger than Earth. So maybe they grabbed some gas, but like not a lot. Right? So even planets are on a spectrum. Right? We're talking about, you have these terrestrial-like planets. They get big enough, maybe they grab a little bit of gas and they form, I don't know, mini Neptunes. Whatever you want to call them, I don't care. Okay. This is, oh yeah, this one's really fun. This is HR 5183b. Okay. It gets real close, and then it goes away. So that's the solar system for comparison. That's Jupiter and the, come on now. So it gets closer than Jupiter, which, not so bad. Jupiter doesn't get super close, but it kind of flings it way out, right? Pretty wild.
Because it's going too fast, or?
Yeah, I mean, something probably happened to it. We don't quite know yet in this class how that happened, but the planets move around, right? Okay. This is another one. This one's really fun. This is the first one. The first weird one that I learned about was HD 80606b. And this is this object, they're modeling the winds because we can actually tell based on when it's in front versus behind how bright or dim it is as it rotates. What I mean by that is when it passes behind and when it passes in front, it shows us a different face. And they modeled that shape and saw that there are these massive winds. And the reason that there are these massive winds is because it essentially does that. Okay. So it goes out sort of towards the location of us, and then it goes way in, basically touching its planet, and then heads back out. And it drives these massive winds on the entire planet. It's HG 80606b. Okay. This is TRES 2b. This is the darkest known exoplanet. Sick, right? It reflects only 1% of all the light that falls on it. If you were here for Alien Day, what could this be? A little what? A little hideout spot? Yeah, well, so remember we were talking about a type 1 civilization, one that uses all the light that falls on their planet. Pretty close. Is this a type 1 civilization? Not quite. We probably didn't get that lucky. It's probably just dirty, Probably just has like a lot of like burn material on its surface. Okay, when you burn something, it gets very dark. So if you make a magma surface and then you let it cool, it'll stay dark. Okay. Could be though. You never know. This is the we saw the system before. This was the directly imaged system here. So what you can see is now we're quite familiar with finding these objects. This is the distance, so 20 AU is about 4 times farther than Jupiter. And you can see just this distance here is about 4 times farther than Jupiter. So it's a very distant planets. All the planets are very far from their parent star, right? And they have this really nice little ring around here. That's probably an asteroid belt or a debris disk from either not forming a planet or continually breaking that planet up. Make sense? Okay. Kepler 36 system's really cool. It's very tight-knit, very close friends. They have the closest spaced orbits that we've ever confirmed. At closest approach, the two come within 1.2 million miles of each other. That would be only 5 times farther than the moon. Now, the moon is small, but it appears big in our sky because it's close. So if 2 planets were at that same distance, it would appear massive in the sky. They don't sit like this, but they come close to each other. Okay. We find them around Knot stars. So pulsar is actually the first place we ever detected an exoplanet. And this is the pulsar B1257+12 system. I know, super helpful. This is an exploded star. And we can see a planet. So the planets sometimes survive after the star does not. Kind of wild. If you're curious about what a pulsar is, we can talk about it at the end. This is the oldest planet we've ever found. It's nearly 12.7 billion years old. Star is dead. This is another pulsar. Yeah.
Do they still orbit the dead star?
Yeah. Well, I don't know. It's probably a gas giant. There's probably nothing living there. This happened 12.7 billion years ago, so very little galactic recycling had occurred, right? So there's probably no terrestrial planets in that system. There's probably no asteroids. Maybe you have some hydrogen compounds, but really not a lot of rocks and metals, right? Terrestrial planets are a relatively new phenomenon. Yeah. Well, when I say the word dead, I mean it's no longer undergoing fusion. So it's there, made of mass, but it's not producing light. Or if it's producing light like the pulsars, it's collimated because it's only burning in a certain direction for reasons that we can't get into. The perhaps sadder planet are the rogue planets. Okay, this is a real phenomenon where some planets get kicked out of their solar system. I know, it's okay. So we talked about this when we talked about the migration of the planets and the heavy bombardment, right? So we may have started with 5 gas giants, right? There's plenty of simulations that we worked on where one of those got thrown out of the solar system. And if that happens, then they just go off forever. They're just floating. I know it's this one's sad, right? Because like, can you imagine like you and your whole family, and then you just get thrown off for billions of years? I mean, you die, but obviously. Okay. We got time. Okay. This is the distribution of some orbits of exosolar planets. So this is like the average distance versus the eccentricity. Okay. So here's 0. That's like perfectly circular. And then these ones are more eccentric. So this is like a comet. Right? These are all comet-like. And the size here is shown in the size of the dot. So Mercury is very eccentric in the solar system, but it doesn't weigh a lot. So it's a small dot, right? The rest of these, like, this is the whole rest of the solar system. All down here. And yet all these planets that we're finding, they're way, way up here, right? So most of the planets detected have orbits smaller than Jupiter's. They're very elliptical. Does this tell us that all planets tend to be at distances smaller than Jupiter? Okay, just the ones we found. But what's wrong with what we're doing? What's the Yeah, we're looking at the ones closer to Jupiter. Those ones we can see, right? So the basic idea is, where does a drunk person look for their keys? Under the stoplight, right? You look under the light, right? Because you like can't see anything else. You're drunk, you're looking for your keys. You look under the place there's light. Okay. So in this particular circumstance, how long does it take for a planet to go around something that's say the size of the Earth? Like sorry, the distance of the Earth? Takes like a year. So I have to watch for a year. Right? If I'm trying to detect something out at Uranus or Neptune, I might need to watch for 20 years. I haven't watched that long yet. Right? So we are going to continue to push observations in this direction as we watch for longer. It's obvious when you think about it that we would find the small stuff quickly, stuff that's close to the parent, because we can watch it fast, right? 120 days, we took the whole observation, we can publish the paper. If I have to wait 12 years, I might be dead, right? Someone else is working on it, right? Okay, so we'll continue to find stuff here. This is an example of a selection bias. Okay. Let's do one more, and then I'm gonna get out of here. Okay. Most of the planets detected have masses greater than the Earth. Why is that? These are all the planets, by the way. Well, as of 2015. It's a while ago. So this is mass, large masses. Here's us down here. Yeah. So you think this represents nature correctly? Yeah, the way I said it is maybe loaded. But let's think about the last one, right? Do we really believe that most planets form closer than Jupiter? No. But we do see them first, because that's the place that we can, right? That's the place the light is shining. We have the opportunity to see them first. If we could wait 50 years, then we'd be able to see all of these dudes too, right? Let's remember that Pluto never made it one entire orbit since being observed, or since being found, right? We found Pluto in the late 1800s. It didn't even make one full rotation. So if we want to see stuff out to Pluto, you have to wait like 240 years, right? You're never going to find planets out there unless you're looking by direct detection. Okay, so is this one sketchy at all? Yeah.
More bigger planets and bigger, more that it's easier to actually spot and it blocks more sunlight as we look around.
Right, yeah, so that would be like the radius, exactly right. But also remember the way that the Doppler effect worked. The more massive ones pull more in their stars, whereas the smaller planets pull less. They're harder to find, right? So this, again, another selection effect, right? Planets with larger masses create large movements of the star. That doesn't mean it's representative. So we saw tons of examples today of hot Jupiters and not so many examples of rocky exoplanets. Does that mean we're not going to see it? No, it just means we haven't gotten there yet. Okay, so this is the missing data found by the Kepler satellite, right? And that looks a lot better. This is the same data taken afterwards, after I add the Kepler data in. And the way you want to think about this, every time you see a star that looks something like the sun, probably 1 in 5 of them have an Earth-like planet, a rocky exoplanet, right? So we go back to that concept that we were talking about before. How many possible civilizations could there be? All you need to know, how many stars look like us, and about 1 in 5 of them have rocky planets around them. Not in the habitable zone, just around. Okay. Questions, comments, concerns? Okay, I need your clickers on Thursday. And then I will provide you with the homework that will be due next Friday, tonight. Yeah. No.
Oh, I should probably get some Alex and come back.
Yeah. Okay. Yeah.
And so I haven't done, but it's my check in with some of with all. Okay, but I was just trying to make sure, I know, I'll probably just explain it in my, either in an email or like in my submission,
Yeah.
to explain my. Okay, like I know it's not a lot.
Yeah, that's fine. Yeah. It is what it is.
Yeah.
Yeah.
I'm sorry.
It's life. Life gets in the way sometimes, right?
Thank you.
Yeah, yeah.